Hello everyone. I'm going to be talking about the three-body problem today. If you know me, it's something I'm interested in. I've been looking forward to for the whole marking period, so this will be fun. So the way I'm going to structure this is this PowerPoint, I'll give you some context behind the three-body problem, what it is, first of all, what we need to know in order to solve it or at least attempt to understand it. After that, we will do a live demonstration right here on the board. Ideally, I would just be the scribe, and you guys would be helping me through the derivation of the differential equations that we use to model the three-body problem. And we'll talk about the existence of a solution, and the question mark is there is because we're not sure if a solution exists, and that's something that we'll explore later. After that, I'll show you a cool computer simulation where we can get a look at how the three-body system behaves, and then also understand its sensitivity to different initial conditions. And after that, just to understand your learning, see if you have any questions, I'll be giving you an exit ticket. So this will be fun. So first of all, what is a three-body problem? This is a quote, and I'm just going to read it word for word and then ask you to interpret it. Given the quasi-steady orbital properties, which are instantaneous position, velocity, and time of a group of celestial bodies, predict their interactive forces, and consequently predict their true orbital motions for all future times. Does anyone just want to throw out what they think that means? I really want you to take a guess. If it's wrong, that's fine. Ted.
Is it like, suppose we have, like, I don't know, we have the moon, the earth, and the sun, and depending on their mechanics, on how they're moving, or, like, yeah, moving, I guess, can we predict how they're going to move at any point in the future?
That's good. So that's a good example of a three-body system that we're all familiar with, the moon, the earth, and the sun. We're going to look at more chaotic systems than that. It's more stable, but it's still definitely a three-body system. And the key thing there is that we're trying to model its position with respect to time. And that's not a trivial task, as we'll soon find out. But it's pretty cool, I think, that we can just say, okay, at time t equals 1, the moon is at, and then give x, y, and z coordinates, the earth is at x, y, and z coordinates, and the sun is at x, y, and z coordinates with respect to, a certain coordinate frame that we're going to set up. So yeah, that's the problem. That was well articulated. And here we are. So I'm going to let this loop for a bit, and I want you to tell me your observations. So the three bodies in motion are the ones that are moving. This point in the middle we'll talk about later. But I just want you to throw out, what do you see? Do you think it's cool? Is there any observation that you'd like to make about this? Tej.
Does the perimeter of the triangle stay the same?
So that's a good point. The triangle is being traced out, and I don't know the answer to that, but my guess is no. And the reason for that is that there's nothing that's saying that the bodies have to stay a specific distance away from each other. But good point about the triangle. And we'll be using that triangle later during our derivation. But those triangles, what are the sides of that triangle? Those obviously doesn't exist in space. This isn't connected by a string. This is a force acting between. But what do you think that the sides of that triangle models? Distance between the bodies. So the red body and the blue body, the distance between them, that's a line, and so on. But it looks pretty wild, don't you think? One could say it looks chaotic. And in fact, that's what physicists say. It's chaotic motion. And that just means that it's the differential equations that model this motion are very, very sensitive. So small changes in the initial conditions as well. And you'll see in the live, you'll see during the simulation, small changes in initial conditions can have vastly different outputs. Where it's sort of like, if you imagine, I guess, a memory, the computer, or not the computer, the bodies sort of forget their initial conditions and start just going very different from what you'd expect. And there's examples of other chaotic systems. Some of you may know that I've also done some stuff with the double pendulum, which is another very cool chaotic system that we can look at, but this is the one we're looking at today. So what information do we need to track positions? Number one, we need to set up a coordinate system. And for that, we're going to use barocentric coordinates. So a barocenter is a center of mass and the point about which the bodies orbit. So we're going to go back to this visual here. This is the center of mass right here. and it's also the point about which these bodies are orbiting. And what's important is that the center of mass is remaining fixed with respect to the orbiting bodies. And there's a few ways to prove that. One that I've looked at is that essentially you find a way to model the center of mass, obviously through the formulas that we've all worked with in Physics 1 and Physics C. And then you find a way to show that the acceleration, so you take the second derivative of that, and then you set it equal, you find a way to show that the acceleration is equal to 0. But another straightforward way to show it is conservation of momentum. This holds true because of conservation of momentum. And we're going to define positions with respect to the barycenter. So we're going to say that, for example, the mass that's tracing out the red path is, let's say, R1, a vector R1 away from the fixed center of mass, which is essentially our origin. We also need forces to track positions. The reason why we want to use forces is because forces encode information about acceleration. And acceleration is what with relation to position? The second derivative of position, the second time derivative of position, which is definitely a quality we want to exploit because ultimately our goal is to find a way to show the positions of these masses. So force is definitely something we want to use, and we're looking at the gravitational three-body problem, which means that gravitational force is what acts here. So gravity is the only force. We're going to consider a closed system where, like we said, momentum is conserved. And for each body, the two other bodies contribute to the net force. So let's go back. I'm going to keep looking back to this because I think it's a good visual. So for the body that's tracing out the blue path, the body that's tracing out the red path and the body that's tracing out the green path contribute to the net force in the same way where, for example, with the moon orbiting the Earth is contributing to that gravitational pull, and then actually the same way, so the moon contributes to the gravitational pull on the Earth as well. So that's really what's going on here. And by the way, this occurs because these masses are very similar. If you have one very, very large mass, for example, the sun at the center of the galaxy, or at the center of the solar system, then you're not going to have this kind of behavior because the mass is so large that the force that the other masses exert on it are much smaller. So that does not allow for behavior like this. And a similar thing goes for why the Earth, Moon, and the Sun is a more stable system. But yeah, our approach is we're going to write differential equations and then we're going to solve differential equations to obtain, ultimately, like we said, position. We're going to find functions to model position. The second one is kind of a hope. First, we need to write up those differential equations, and we need to see if we can solve them. So with that being said, I'm going to hop into the live demo. I'm going to grab a marker here, and I'm going to draw a bit. But in the meanwhile, does anyone have any questions about the context? Maybe something about the history as well?
What's the history about?
I mean, Newton studied this problem, and over the years, there's also been a lot of cases where, spoiler alert, you can't solve it. Sorry, spoiler. I mean, it's commonly understood, but there are particular solutions that you can solve. So, for example, there's periodic solutions that people have found. And there's also a Pythagorean solution where you put the matched ratios like 3, 4, 5, and then specific positions. So there's different instances, and people love solving this, solving different cases of this and finding different particular solutions, but there's no general closed form solution to this, which I think is pretty fascinating. So maybe I'm going to draw this a little closer here. This is the first mass, M1. Let's draw another mass, M2. And I'm going to draw a third mass, M3. 3 masses, 3 bodies. The first thing I want to do is what? We talked about barycenters, right? So where should I draw a barycenter and why should I draw it? Sam?
Can't you just I mean, it's a pretty simple picture, so you can just either use an equation or probably easier just draw it and put it in the geometric center of it.
Right. So here I can say roughly the geometric center, and I want to use this because this is the way I'm going to define the coordinates. So this is 0, 0, 0. Sedge?
Do we know the masses? Are they
So the
equal?
masses would be known. Right now we're going to do this generally, and it's also important because, well, I mean, if you're solving this in a general form, then you leave the masses in an ambiguous case. But for setting up like certain particular solutions and trying to understand like the motion of bodies with, for example, different certain mass ratios, maybe like we said, the Earth, the Moon, and the Sun, then you're going to know the masses when you're visualizing the system. But here we're going to leave the masses ambiguous. So yeah, this is the center of mass.
If the mass are ambiguous, how can we say that the center of mass is there?
Well, we can't. So this is a representation. We can't say where exactly the mass is, or the center of mass is, but obviously it's going to lie within, contained within some triangle. But yeah, that's a good point. So it need not be here. If the mass ratio is a little more, let's say m2 is greater, then sure, it can be here. For now though, in terms of pure representation, it's perfectly equivalent to say that it's here. And that just helps our sensibilities, I guess. So I'm going to do one thing here, which is, actually, I might want to switch colors just for clarity, if this works. Here we go. So this is the distance from the center of mass, that origin point, to the first mass. And this, I want you to think of as a vector directed from the center of mass to the first mass. And we're going to call it R1. What should I do next?
Make vectors going to M2 and M3.
How do you think of that?
Just a geometry.
And there we are. So these are absolute positions. But what do we know about gravity? Can someone throw out the law of universal gravitation?
G over R squared.
Well said. Also, going forward, someone other than Sahed, she's talking too much. So yeah, we say Fg equals G m rotation over R squared. That's what we say here. I'm going to amend that a little later, where I want to represent it in a different way, in a more like form that's suited towards vectors. But yes, so this is the universal law of gravitation, and this R right here, what is that R?
That's the distance between the two bodies acting between.
The distance between the two bodies. So is this any good to us if we want to find the distance between two bodies? You're shaking your head. Why is that?
Because that's not the distance between two bodies.
Right. So these are absolute positions, but they are vectors, so they still do encode information that we can use. And that I will show with do these work?
Probably not.
Okay. Cool.
You test and see.
Prayers. Oh wow, look at that.
There's a green marker here that works well.
I thought we didn't use green here.
Sorry?
Nothing.
You don't want to use green?
That's up. Thank you. So yeah, we'll switch to green just for clarity. So these are the resultant vectors, one could say, from a particular vector addition, which we'll talk about. But that, and again, this is a vector from M2 to M1. That's the way we're representing it. But what is this length? How do I find this vector? Someone from this side. So like, the first thing we learned in physics 1. It's a hedge.
You can split up like the R2 vector from the center to M2 into its horizontal and vertical components.
Actually, we don't need to split it into components, but we do need to do something. I want to label these. Did forget to do that. We do want to do something with R1 and R2.
Can we use the Pythagorean theorem to find?
We don't need to actually split it into components, but you're right in thinking of a vector addition. But my question is it a vector addition or a vector subtraction?
It's subtraction because R2 is going from the origin of the center of mass down to the point, so you have to subtract it.
Yep. That's a good explanation. If you want to see that visually, if I draw R1, this is R1, And then R2 I negate so that it goes this way. Because currently it's a vector directed towards M2, so the arrow's pointing this way, and I negate that, so it goes that way. Then what we're going to end up with is what looks like this resultant vector here. So that's the reason why it's vector subtraction and not addition. Addition would give you a vector that's not this, and we're going to follow that line of reasoning if there's an eraser somewhere. So we're going to follow that line of reasoning to write up these relative distances. So the distance between M1 and M2, we're going to write up as R1 minus R2. And this is vector subtraction. So that means that it's not like you can't just subtract the magnitudes. You have to split it into its components and then do that process, which all of you are obviously familiar with. And the same thing goes here. So here we're going to have R1 minus R3. And here we're going to have R2 minus R3. And all of those you can verify again just by the same visual idea. But now we have distances between masses which we won't need for using gravity. So what's my next step? Derivation ideas. Yes?
I would use like two of the masses and the radius between them and try to solve it with the gravity.
Right. So we're going to write three, all of us know F equals ma. We're going to write three F net equals ma equations. So the first one is going to be M1. I'll stick with the red. Actually, let's go. First one will be M1 times its acceleration, which is A1. And one thing I want to do, so notation-wise, I actually don't want to use A. Are you guys familiar with dot notation? So yeah, so we're just going to use dots. So R is a position, R dot is its velocity, and R double dot is its acceleration. So here, M1A, we're going to write as M1 R1 double dot. So that's the way that we're going to represent this acceleration. And this, we're going to set equal to two things. Remember during our demo that we said, or rather our context, that we said that for each body, the two other bodies contributes to the net force. Here, for M1, what are the two other bodies that are present? M2 and M3. See, people participate now. So M2 and M3, we're going to consider the gravitational force that they have upon M1. Before we do that, I want to amend your understanding of the force of gravity. So we were used to writing this, and this is fine, but for vectors, there's another representation that I think is just a little better, which we're going to use. So here, I'm going to write, so the force of gravity in the x direction we can write as the same GMM over, and now we're going to say the absolute value of r cubed times some vector r, and that's that's a unit vector, so that r hat 1. So here's a visualization of that. If this is the first mass, and this is the second mass, then you'll realize that these r's cancel. But the reason that we do this is that this also allows us to say something like, okay, the force of gravity in the x direction, sorry, this is the r direction, but the force of gravity in the x direction, so the x vector, the x component, can be written as g times m1, m2 over r cubed times x, so that x distance, or where the x distance is, when you split these into components, the absolute distance in the x direction between these two masses. So that allows us to write the force of gravity in vector form, which is particularly useful when we do the computer simulation. So that's just how I'm going to write this. So we're going to write r cubed times r. So just wanted to run that by you. But now we need to write up two different forces. So m1 r1 double dot is equal to, give me the first one.
F of M2 minus F of
I want you to say it in terms of gravity. So I use the universal law of gravitation to give me two different forces. Just give me one though. Hint, it's the gravitational force between M2 and M1. Let's start there.
Yeah.
So G M1 M2 over.
Let's speak up just a bit.
Oh, sorry. G M1 M2, and then I can't really see what's supposed to be under that.
Here?
Again? Yeah. Or below that.
This is R cubed.
R cubed.
So R is the distance between the masses.
So then it would just be that number.
that R1 minus R2.
Yeah. All cubed, and then you have
Times R1 minus
Yeah.
R2. But yes, very good. So if you guys didn't hear that, and maybe this will help you, G M1 M2 over R1 minus R2 times R1 minus R2. So that is the way we're going to write
I
that.
think
So
we're
Yeah,
going
just
cubed here. Well said. One thing though, technically this is negative, and that's because M1 is being attracted towards M2. So we're going to assign a negative sign to that. So in other words, M2 is pulling M1 towards it. It's a force of attraction with gravity. So we're going to assign negative signs to that, just a little note. And can someone now give me a similar form equation, or a similar form representation for the force between M1 and M3? Girish?
Negative G M1 M3 over the magnitude of R. Yeah, whatever.
Yeah, I got it.
Okay.
Times?
Times that.
Yep. That's cool, right? So the force, the net force acting on the first mass is the gravitational force from the second mass plus the gravitational force from the third mass. It's pretty simple when you think about it. Once we got the representation down and we actually got understood the way that we can write these vectors, this is really easy. So that means that you guys can do the other two, right? All right, let's do it. Someone has to read it out for me. I refuse to do this myself. So here's M2 right here.
It would be G M1 M2 over.
Just remember the negative, but yeah.
Oh, yeah, sorry. Negative G M1 M2 over. I can't read it from up here, but yeah, that
Yes.
one, yeah.
So I'm glad you said that, but it's actually the other way around.
Oh, yeah.
Since we're going from here to here.
Yeah.
But right.
Yeah.
So over R2 minus R1
Cubed.
cubed. Yes, thank you.
And then that again is
Good. Now the other one. Want to give it a shot? Someone else?
G M2 M3,
Yes.
and then divided by R2 minus R3 absolute value cubed times R2 minus R3.
Excuse the handwriting there. But yes, that's the second mass. Now the third mass. So following our inopportune interruption, which is pretty funny, here we are with two equations. Since we're pressed for time, I can write out the third, I guess, but ideally we would have done it together. So this is for the third mass. So it's acted on by the first mass and the second mass. So it's going to be a negative G M1 M3 over that makes sense. And similarly here we'll have thanks for joining us, Ed.
Oh, of course. Wouldn't miss a syllable.
there we are. So 3 equations for 3 masses. One thing that we can do, since we're concerned with acceleration, is we can go through and cut out our m1s, and that just leaves us with what we have here, and we'll do the same thing here as well, and here. So these are second order differential equations, and the thing is, we don't know a solution for them. So in other words, there's no like commonly understood function that exists as the antiderivative of these functions right now. And does anyone remember when we can't solve a differential equation, one of the ways that we look at it?
We plug in points that we do know to come up with a particular.
So that's true. So we do have initial conditions, but that just makes it a particular differential equation. Or yes, but what do we do when we don't know the integral for a function, but we still want to understand how it behaves? It's a method of approximation.
Euler's method?
Right, Euler's method, which is actually a part of a family of many approximation algorithms. But Euler's method basically says that you can approximate with like small tangents. So you have the line y equals 2x, which is the derivative of what? X squared. So you can approximate, obviously you know the antiderivative of this, but just to show you, you can approximate with like very little tangents, so very, very small tangent lines like that. You can kind of approximate the curve. And then as you make that delta x smaller, you can sort of get an image of what the curve is. So that's what we're going to be exploiting here. And obviously it's very tedious to do it being a human being, especially because we want small enough time steps so that the distances look convincing. So it's a more accurate representation. It's sort of a good way to think about it is that we are simulating what's going on here. So these differential equations are modeling phenomena, and we're saying, okay, so let's just step through a situation in which these situations or these differential equations are acting on certain masses, and then see what the position is, rather than having like an objective function for the position. So the way we do that efficiently is with computers. So what I have here, ideally this would run. Is a sort of simulation. Let's give it a second starting the session. But this is Python. And what it's going to do is it's going to give you a little plot of a visualization of these equations for particular initial conditions. So like, you know, we pick a very specific mass and set it at a very specific position. And there we are. Pretty crazy, right? Oh dear. Can I not just refresh? Let's try that again. But yeah, so here, it's actually a rather straightforward process where you just write out these equations into the computer, and then you write out the Euler's method of approximation, or use a library that already has Euler's method written into it, and you can do a numerical integration. So actually a pretty smooth process.
So this is just like basically a really complex calculator is what you did?
That's true, that's a good way to put it. It's just a calculator. And so just to give you an idea of how small changes in initial conditions can change the way that this behaves, this is another solution. Here you see some of that periodicity hedge that we were talking about, where like these masses are going off, and this third mass is being ejected from the system. So Sam, remember we discussed this, right? So it's pretty cool that, and this is just a very tiny shift. In fact, it was completely random, where I started out with the first one, I'm like, hey, this looks cool. Let me tweak these numbers a bit and see what happens. And this is what happened. So that gives you an idea of the sensitivity. Any questions on anything I talked about? What are your thoughts? You think it's cool that we study this stuff?
What are the Sorry, what are the applications for this?
I don't know. In terms of application, I mean, if you're talking about in general simulations, then it goes a long way. But if you're talking about this specific problem, we study it because there's planets that, or bodies in space that behave in such a way. There's systems and star systems that we want to understand the positions of and different things with. And having a general solution is a big push that some physicists, specifically in the astrophysics community, are working towards. And there's new progress being made, actually, especially recently. There was like 200 new particular solutions found. But again, not a closed form solution yet. So it's a field that we're still working in. Tej?
Okay. This might be a stupid question, but can the three-body problem involve more than three bodies?
Good. It's called the n-body problem, where like you have n bodies. And yeah, absolutely. It just becomes more chaotic. Then you start having different forms of behavior, obviously still very difficult to solve. You can find tons of little animations on YouTube for it. You can also learn about it, but this is the basic idea for it. Where now you can imagine if we were to put this into 4 bodies, now you have 3 other masses acting on the net force of this one mass, so like M1, M2, M3, and M4. And that's going to have different consequences as well. So I'd encourage you to look into it though, because I think it's pretty cool that we're also able to see stuff like this.
So once it ejects that third mass, those next, they're not in chaotic motion anymore, they're in repeating motion? Or is it still
So here
chaotic?
it looks somewhat periodic.
Oh.
I'm not entirely sure. So there's also a 2-body problem, which is more stable. So yes, to answer your question, it's not. There's no like defining line for what chaos is. I guess it's more visual. So like, does this look chaotic or does this look chaotic? This looks chaotic, right? Looks crazy. So that's where we draw the line. But yeah, it's more stable in the other case. I mean, there's other examples of chaos theory as well. So the double pendulum, for example, which I've talked about today as well. But that's another example where, like, you know, when you have one simple pendulum, you can find the period very easily. You can understand how it moves very easily, just back and forth. But then you add on another mass to that pendulum, so you have 2 rotating arms, and the motion just becomes crazy. If we had time, I would show you another simulation that I did with the double pendulum. But it's crazy how it operates. I think that's again something else that you should look into. And the differential equations for the double pendulum look a lot crazier than this, which is actually I decided to show you these instead of that one, since that requires like Lagrangian mechanics and other stuff that we didn't yet talk about. So then, yeah, thank you all so much, and